Welcome to Cookie's Maths and Science Hub. Today we'll be exploring the concepts of work and power. What is work? In physics, we say that work is the measure of energy transfer when an object is moved by a force over a distance. Whatever the situation where we say we are doing work, there are two features that constitute the amount of work done. The amount of effort required, or the force, and the distance or displacement of the object on which the work is being done. Work is a scalar quantity and is measured in joules, represented by the letter J, capital. We have a few formulas we can use for work. That is, as we've stated, work is equal to force multiplied by displacement. Therefore, the amount of effort required and the displacement on the object done. We can also say work is equal to the change in energy, as we're measuring the change in energy when we talk about work. We'll use both of these formulas in some problems in this video. Power, on the other hand, is simply defined as the rate at which work is done. That is, power is equal to work over time. Remembering time is in seconds, work is in joules, and we represent power in watts, represented by the letter W. Got to be careful not to get it confused with representing work. Power is also a scalar quantity. Here you can see two simple examples of problems using the equations we have discussed. We're asked how much work does an elephant do while moving a circus wagon 20 meters with a pulling force of 200 newtons. So we know that work is equal to force multiplied by displacement, which means it's 200 multiplied by 20, which gives us 4,000 joules. Remembering it's important to include the units. We're then asked if the above took 5 seconds, how much power was generated. We know that power is equal to work over time, which means our power is equal to 4,000 divided by 5. So in this case, 800 watts were generated. Being careful again to include our units. From these simple problems, let's look at a far more complex problem with multiple more steps involving work. We're asked in this question, a 7,000 kilogram car traveling at 20 meters per second comes to a stop at a set of traffic lights over 50 meters. Find the force of the road applied to the car during this time. So, in this case, it is a work question, but we're not looking specifically for work. We're asked to find force. Looking at our work equations, given that I promised we're only going to use these equations, well, maybe we'll use one more, but I'll discuss that shortly. We're using these equations mainly, so which of these equations includes force? Well, we can see it's our first one. Work is equal to force multiplied by displacement. So, to find our force, we simply divide both sides by our displacement, and we get force is equal to work divided by displacement. However, you'll notice in this question, we don't have work. We haven't been given work. But what have we been given? Well, let's have a look. We've been given our displacement, 50 meters. So we don't have to worry about our S. We can put that in later. We haven't been given much else really. We've got the weight of the car and the speed the car is traveling at. Now, this means you'll have to remember back to your energy equations and remember that something that is moving has kinetic energy. If you can't remember that, I suggest checking out our energy video. Now, if that means it has kinetic energy, we can use this to calculate the energy of the car. Now, given that it's coming to a stop, the change in energy is simply going to be the energy it had to 0, meaning it's just going to be the energy it had is the amount that it changes by. Given that work is equal to change in energy, we can have force is equal to change in energy divided by our displacement. So, let's have a look at our kinetic energy in this example. Okay, so our change in energy is our energy final, take energy initial. Now, we're looking for our kinetic energy, and I've included the equation over here. Our energy kinetic is equal to half mv squared. Half times our mass times our velocity squared. Now, in this case, it's going to be negative because it's going to be E final, or our final energy, subtract our initial energy. So we're going to have just that subtract our initial energy, as our final energy in this case is 0 because the car is not moving and it has no potential energy because it's not elevated. So writing that out, we have force is equal to negative half mv squared over our displacement. Now we have all the information we need. We have our mass, we have our velocity, and we have our displacement. So let's plug it all in and see what we end up with. So we have negative a half times 7,000 times 20 squared all over 50. Which gives us negative 28,000 newtons in the direction of motion. Remembering force is a vector quantity, meaning we need to include that direction. Now we don't have a set direction in the problem, so we're just going to say in the direction of motion. Now this makes sense that it's negative because that force is applying against the car, slowing it down. You can see that whilst the work equations are quite straightforward, they often end up incorporating other equations to do with energy because of that change in energy that work is equal to. So it's important to know your energy equations when working through work and power problems. Thanks for watching. Hopefully now you have a good idea of what work and power are and how to solve for them in a variety of different problems. Be sure to leave a like and comment for future topics you'd like to see explored. Hope to see you back again soon.